So, hi everyone. I'm Colton. I'm with Next47. We're a VC firm, and tonight, as VCs tend to do, I'll be asking a lot of questions of people much smarter than me. So we have some great panelists here tonight across, robotics, software, and foundational models. Maybe we could just start off going down the line, and if you could just introduce yourself and what you're doing.
Okay, I'm Kalpana Seshadrinathan. I'm the head of deep learning at Skydio. Skydio is the largest US-based drone manufacturer, and my team works on all the deep learning-based models that we deploy on the drone. My background is in computer vision and video processing. I have a PhD in the area, and I've been working in the industry in the Bay Area for over 15 years now.
And I'm Ulrik. I'm one of the co-founders of Encord. We build data tooling and infrastructure for AI development. So we're very fortunate to work with some of the world's top AI teams that are using our platform to develop the data they're using for their AI models. I have a computer science background, not a PhD, but I've worked on a number of different types of deep learning projects through my career. And of course, started Encord a couple of years ago with my co-founder Eric, who's based in London.
My name is Ivan, and I'm CEO of Archetype AI. It's a relatively new company. We've been operational for about a year. It's started by 5 people leaving Google, and we're building a foundation model for sensor data. Basically, think about like ChatGPT, but for physical world sensor data. And the observation, when we were at Google, we actually working for hardware division. We're building sensor solutions for all consumer electronic devices like phones. Pixel 4, the best phone, by the way. I was working on that, and then home devices, all of that. And so building deep learning techniques, deep learning models for the sensor data is what the team was working for 8 years before leaving and starting a company to build a foundation model that can rule all the sensors in the world.
Hi, I'm Stefan. I'm actually part of the latest moonshot of Google, which made it become an independent company, but independent. This is so overrated. We still belong to Google, and independent company within the Alphabet empire. So Intrinsic is essentially looking into build a generic Robotics platform, which has everything from real-time control to cloud-based management to AI, machine learning, perception, research, production quality, software and hardware that can be taken out into the world. And it's a long path to get there. Just as a background, I'm actually originally an academic. I've been a university professor for over 20 years at Los Angeles, the University of Southern California, and also for 10 years at the Max Planck Institute in Germany, and lots of other things in between. But for 6 years, I have been actually part of the Intrinsic world, which is a huge amount of fun, and I think it is new world pretty well.
Awesome. And I'm honored to bring up the rear. So my name is RJ, the co-founder and CEO of Maniro, which is an early stage robotics startup. We are applying the latest in our generative AI techniques, but to robotics into the real world. And it started with actually strawberry picking as our first application. My background is been in robotics and self-driving for the past decade or so. And so we decided that, maybe a slightly less safety critical task like agriculture or strawberry picking would be the easier place to apply some of these techniques. So happy to be here, and thanks.
Great. So maybe we could go back to RJ and go back down the line. The common thread here is physical AI. How would you define physical AI?
I guess the phrase itself backs up in the question. It's only you need to be applying it to real world, and taking it off of bits into atoms, and actually I think making meaningful impact in activity out in real world. I think at the same time it has come in many different terms, whether that's this AI. I think that's the latest incarnation of previously was embodied AI. Maybe it was a little bit too complicated. But I think we all genuinely have that the intuition of it making some meaningful impact in the real world as opposed to just in the digital space.
Stefan?
Okay, yeah. So I will just add to this. So physical AI is basically about physics. What is physics? Physics is about stuff like Newton and Euler and forces and torques and inertias and all those kind of things, and about devices or systems which interact with physical world. And the fun thing is, this is incredibly harder than creating something on a web browser. And just from a machine learning point of view, just like this wonderful example. If you get machine learning high-order, it's 90% accuracy in cancer detection. People will love you. Okay, it looks fantastic. If you have machine learning algorithm, which makes your robot fall over 1 out of 10 times when it gets up out of its chair, you are dead. Or the argument would weak you out. Easy. So it's a totally different domain. The physical domain is way more stringent than that, what makes actually physical AI very different beast than many of the other machine learning techniques.
Yeah, we think about physical AI as a basically a general purpose intelligence which can quote unquote understand physical world. And the biggest question is, what does it mean to understand physical world? It's a very complex thing. People have been arguing about what does it mean to understand physical world for like centuries. You can argue that physical world cannot be understood at all, and there's argument that physics does not exist, by the way. And all the sort of arguments have been going for a long time. So the way we define it, in our company, we define it very narrowly. The way we know that the world exists is through senses. Humans have a natural senses, which is eyes and ears and touch and smell. And we have an innate capability, evolutionarily developed, to fuse those sensors together and give us a picture of the physical world, which allows us to perform reasonable, kind of like self-guided actions. And also we're able to transfer knowledge by learning how the chair works here to any other chairs of the world, right? So this kind of generalization capability is very important. We would like to build a system which can have the same generalization capabilities, and by learning a few senses for one task or one conditions, be able to expand to the rest of the senses never been seen before, tasks never seen before, and be able to understand the physical world directly from a variety of sensor data. What's exciting about it is that I think this physical AI space is very much focused on vision, computer vision, which I think is a big mistake, because if you look at the like real world applications, most of the world is not run on cameras. Camera is only one of the few sensors. It generates the most data, but it's not the most, I would say, even valuable sensor in the say industrial setting. The old rigs, we having conversations, for example, with Slumberjee, who's doing horizontal drilling and collecting a huge amount of sensors. They don't have cameras to control the horizontal drill in a well, right? They have like a bunch of other different sensors, right? So what's exciting about physical AI compared to humans is now we can build AI which can have sensing, which humans don't have, like radar vision and feeling temperature and anything. Like all the sensors can become possible, and we can fuse them together to create a completely new picture of the physical world, which humans don't even understand. And I think that's kind of this kind of physical AI would be a companion to human and make us smarter, because we'll be able to see the world in the way people don't. That's my long-winded answer.
I thought that was a very good answer. Yeah, I think it's very interesting to think about physical AI in the context of like where we are in general AI development. So the last 10 years have been about building AI systems that can understand the digital world, essentially, which is images on the internet, code, text. And I think the next decade is going to be basically like grounding AI systems in the physical world, which can be systems that can reason, perceive, and act across like all the different types of sensors that the rest of the panelists have described. And I think that's something we're extremely excited about, because I think those types of AI systems are inherently multimodal, which adds, I think, a lot of interesting development complexity, which for developer tooling a company like ours, of course, is something that we thrive on.
So I think I'll follow up on the same line of sense, understand, and react. I think that to me forms the basis of physical AI. And just to be kind of tangible, some of the use cases that we have around this is actually path planning. People often think of manipulation as a common thing when it comes to physical AI. Oftentimes, when we are flying in completely unknown in the wild environments, we need to understand the obstacles that the camera, that the drone is seeing, thin wires, tree branches, windows, structures like these, and automatically replan in real time to be able to avoid these obstacles. This is a kind of use case that we care about. And in addition to everything else that was said here, the only other thing I would add is an understanding of the 3D world is quite important when it comes to physical AI. A lot of these existing models, for foundation models in particular, work great in 2D. But oftentimes when we are doing tasks, performing operations in the real world, we need to have an understanding of the position, location, orientation of objects in the real world. And that's a big part of physical AI for me as well.
That's great. Thanks for helping orient us there. I had one last question for the whole panel. What either, for you or in general, is the hardest problem in physical AI that, either people aren't talking about or might be overlooked? Start.
I can start. I think for me, one of the hardest parts is the physical part of physical AI. It's working with real hardware, real sensors, things that need to work under adverse conditions, things that need to work reliably, safely all the time, things that need to have long battery life to be able to complete the missions that people expect them to do. So to me, like the sensors, the actuators, the hardware, and then the real-time intelligence that is needed to operate all of these is a fundamental challenge here.
Yeah, no, I think that's fantastic because I think that resonates with a lot of the stuff that we're seeing, because I think when we work with a lot of different AI teams, what we most often see is the hardest problem for them is closing the feedback loop basically between the deployed model and like wherever like the AI system lives. So like closing the loop between the physical world and your AI system. And that really requires you to have like this tightly integrated feedback loop between like whatever device that you're building and like wherever you have your data and your compute infrastructure and all these things. And it's very easy for digital AI products to do this, right? Because you have a thumbs up or thumbs down and a thumbs up button on ChatGPT, which gives you real-time feedback from the usage of the model. But you don't really have that luxury in physical AI, right? Because you have all the problems you described. You also have like bigger problems with like data accessibility and all these other things. So yeah, that's like the most successful AI teams that we work with are the ones that are like figured out like how to close that loop essentially between the real world and their AI system.
Yeah, I think obviously one obvious thought is that what is difficult about physical world makes physical AI difficult, and I completely agree that in a very kind of operational sense, be able to deploy AI in the physical world solutions where you have, particularly in our case, where we're building kind of foundational platform or model which we can deploy to multiple customers. You have such a broad variety of conditions you need to deploy it. Computing platforms, real time is always a problem, always difficult. Kind of connections you have, kind of sensors you have, all these protocols, so this kind of like messiness of the physical world and the incredible fragmentation of all use cases, that's a critical problem. How to combine this generalization quality of the model with extremely high level of messiness when you go to any kind of physical world environment. So on the practical side, this is kind of is a problem you need to solve. I think on the conceptual side, we're trying to solve many things on high level problems, and the high level problem is that how can we explain physical sensor data in a way human can understand? I think that's something a bit of a gap over there. For example, we're getting a multidimensional signal from 65 turbines collecting 40 kind of sensors and giving this massive cloud of data. And we can do the numerical sense, like we can find anomalies and predict what's going to happen and do all those things using our models, but and give analysis. But now we need to combine it with the standard operation procedures from this maintenance team, from the kind of basic descriptions how these turbines work, and now you need to kind of explain the data in the terms of specialists of the people who manage this electrical turbines. So I think this is a combination of the human understanding, how people think about physical world, which is not physical at all. It's completely, I think, sometimes random, and arbitrary, and actual core physics of the model, which is actually completely predictable and deterministic. This is kind of matching we see as one of the challenges we're trying to solve.
Let me just add a few things to that. AI is the ability of robust generalization. Super challenging, and I think it's completely messy. Just going from one task to a related task without massive data or relearning or whatsoever, what humans can do all the time very easy. There's some abstraction and potentially analytical insights. I don't know what analytical insights actually mean in an empirical way. Most likely some embedding, I have no idea. But getting to this level of robust generalization, you don't have to generalize from whatever electronics manufacturing to tennis play. This is totally relevant. It might be AGI, this is great, but it's not really necessary. Can you just be in a certain domain really competent? But then robustly competent. That means not 60% success rate. You go from 1, 2, 3 shots back to 100% success rate, or you give Betos to that.
Yeah, and I think I definitely want to echo what Stefan and Kalpana said just now. Hey, it really just comes down to robustness and reliability, which is unique for, in the physical world, which folks have mentioned earlier. In many ways, this is one of the most exciting times for robotics in, many decades, right? The excitement and energy with a lot of these generalist approaches or humanoid robots and all that. But at the same time, if you think about it, no one has really actually meaningfully demonstrated that robots can meaningfully be out there in the real world, and that's maybe the exception of Amazon Robotics. And I think it comes down to robustness and reliability, to a point that Stefan and others have mentioned. So a lot of these companies take the approach of, hey, we're just going to do the ChatGPT for robots, and therefore that is sufficient to raise hundreds of millions of dollars or more, right? And I think all of these is let's actually first show that you can do it on one task and do that actually really robustly and reliably. Now, of course, we hope that we can make a good, make money doing that one task. But then if you can show that you can actually do that one task really robustly and reliably, such as actual products that people actually want, now you build out the whole process and infrastructure, whether that's your verification validation systems or the data layer, your software testing layer, to then scale to other applications. So I think that robustness and reliability is something that the devils don't talk about much, right? But as practitioners, that really is where things either successfully fail up or they fail.
Great. Yeah, a lot of interesting points in there. Reliability in the face of challenging conditions, data management. Let's talk a bit about the models. Kalpana, at your work at Skydio, is what role do generative, the recent generative models we've seen for vision, for language, do they play in your technology, if at all? What are the pros and cons, and where do they fall down?
Sure. Yeah. So I think these foundation models, whether it is the vision language based models or the universal segmentation models that we have seen, like SAM or SAM2, I think they've fundamentally changed the way we generate training data for the different models that we deploy on our vehicle. So first, for example, I think it's impossible to see an annotation tool that does not use any of these universal segmentation tools. So tasks that used to take us a long time to do, like drawing very detailed outlines around objects where computer vision was not very good, is sort of solved for the most part, and it's only cleanup that we do in many cases. And then the second thing is generating training data. I think that's something also that fundamentally these technologies allow us to do, which allows us to address corner cases, things with a long tail in the distribution, which is very difficult to capture in real life, and the ability to generate these types of scenarios to incorporate into the training to be able to be robust to those situations. And then the final thing I think is data mining. With these foundation models and the vision language based models, we can now search and mine for semantic content in the different, in the millions of logs and videos and image content that you have, which again allows you to tailor the content that you're using to train your model and find the interesting examples and the relevant pieces of information that you're looking for. And all of this basically also allows us to do distillation or student-teacher types of models where we can train these larger models for a certain task and then try to distill that knowledge down into something. But end of the day, we do operate in real time on the vehicle, and a lot of our models are run at real time rates on the vehicle with embedded GPU compute. And so this does constrain what we deploy on the vehicle. And so there, I think we are still doing a lot of the classical techniques for that.
Makes sense. So you can use it for your data management, but on the edge it's a little more difficult to put a full large visual language model or something on that hardware.
And one more thing, sorry, I'll add is the cloud connectivity with the cloud. And so sometimes if it is not a latency sensitive application, if it is a data that needs to be processed after a mission is completed, data is captured, there's a lot of compute that is available in the cloud that we could potentially leverage to run larger models, but we can't always rely on connectivity. And so we do focus on the edge quite a bit.
Got it. And Stefan, question for you. I know Intrinsic focuses on ASI over maybe AGI. Could you explain a bit more, what ASI, like how would you would define ASI and why that's a focus for Intrinsic?
Okay, now, context. I'm surrounded by thousands of deep miners, and they've been getting on my nerve at AGI as well the last 10 years at ISA. And some point, again, the other group of deep miners were sitting down and say, hey, what are you guys in Intrinsic actually doing? And we said, okay, we've actually wanted to artificial specialized intelligence. And that actually means we don't want to learn the super big models here and everything, which is very admirable to try, but I think it's also super high risk. We would rather learn kind of models which are competent in a domain of focus tasks. One super simple example, connected research. Gets over key orders again. Or you got USB in, USB out, whatever to basis. It has to do multiple times in the industry, it has to zap the right up and down. We made that okay. It is our chess. It wasn't up there in nature. You didn't, you made out all this connected searches about it. It's super simple. It's a part and a common part. You could care. Could you just learn in more to focus on that and be really competent, not 80% performance, but 99 is up to performance that shit. People like me would start be this and that. So this is a little bit what a view like focus on. And I think it's actually important to just say this is a path. Maybe if you do ASI really well, you create so much useful data that AGI becomes a little bit closer. But started from the testing it is, Skydio and was elevated, slightly heavy about me get this. We still need to demonstrate that we have path to revenue at some point, give some people. And being more focused helps to make progress. And speculating on something too big is just super risk. So that's kind of very cover.
And RJ, along the same topic, you were mentioning how you kind of narrowed in on a very specific use case of strawberry picking to start. What led you to that specific choice rather than go start a full, humanoid robot company? And furthermore, are there any models that you found so far, architectures that work best for this use case?
Yeah, so there are a few parts to the question. I think in terms of the use case, right, definitely an echo what Stefan says, focus on to be able to do a task well enough to make it a product and make it a market. Why strawberries? Well, I could go on and on about why there is such a market there. It's very, and from a robotics angle, first there's a huge labor shortage. No one wants to do that task. 70% of your strawberry production actually goes to labor, and we don't really need any VLNs or VLAs, right? Because the only task we tell the robot to do is pick strawberry, pick strawberry, pick strawberry, right? So you only need lightweight instructions, right? So along the lines about the models, sorry, maybe just to wrap up on the business side, it's a nice beachhead for us to approach. Where and it's very concentrated in as far as our application go. It's almost always strawberry is they produce only in 3 counties in the US, in California, 1 in Florida. And from a sort of robot operation environment perspective, it's much easier when you have potentially hundreds and thousands of robots in a single location than to have to worry about, for instance, a robot in every home and you try and support that. And then, of course, in terms of as far as safety critical nature, robustness, reliability, so slightly less safety critical than self-priming, for instance. So, if I kill a few strawberries, really no one cares. So as a sort of use case to really hone our systems, I think that makes a lot of sense. That's sort of models. I think what we see, in some ways, what has powered this latest wave of physical AI or robotic AI is this idea of Gen AI and applied to robotics. What does that really mean? From our perspective, is that the sort of paradigm of doing robotics previously, where you do things like perception, prediction, planning, and control, has fundamentally changed into one that is much more what people have called end-to-end, right, or going from pixels to actions. Now, that brings a lot of advantages, but also risks. Right? Advantages being that you don't need to do many models of every individual component and try to do verification validation on every single subcomponent and deal with every single edge case. You need a different segmentation model, defection model for every single thing. And you can just kind of lump it all together. Now, first, the big risk there is, can you, it now becomes one big box as opposed to many guide boxes that you can sort of at least verify in the subcomponents. And so that, of course, brings with it risk of, can you sufficiently verify it to then deploy a product? But those are some of the things that I think have powered the excitement in robotics today.
Thanks, Archie. Next question for Ivan. So, Ivan, at Archetype, you're working on a physical AI model that's very aptly named Newton. And we heard RJ and Stefan talk about, their focus on, specific domains. You have, a model that, can be applied in a lot of different ways. So how do you think about, helping, being able to work with companies with, very specific kind of domain-based goals?
So we don't do robotics. And as I mentioned before, we are not focused on kind of action planning, like problems like picking up strawberry or doing actions in the physical world. Is fundamentally actions planning tasks. We don't deal with them at all. So we are focusing again on the companies in the world. What happens is that over the years, amount of data being generated by the industries is dramatically increased. An oil rig generates like terabytes of data every day. A car generates 20 kilobytes of data every day. All these companies, and the system becomes so complex that they cannot be described either by digital twin. People try to build digital twin, doesn't really work really well because somebody have to design this digital twin for some factory or for some city, and then small changes you need to go to redesign. Just fundamentally not scalable. So fundamentally, what we have right now with all this companies and our customers is that people kind of are awash with data, and this is physical data, and there is no techniques which allows them to treat this data and kind of like be able to talk to this data, to ask questions about it, to have you have to design basically find like anomalies, ask questions like what's wrong with this data. And we see sort of a broad range of companies going from applied materials to these, the Schlumberger, to the automotive companies, to the industrial construction companies who coming to us with requests. Can we have like one model which we can feed all this data from our construction side or from a machine and ask the questions, what's wrong with this? Tell me when something goes wrong. Because you cannot train model for something model doesn't know or you don't know, but a model which kind of understands physical principles of how data generated, how data works, start learning patterns which repeating over and over again, and start learning how to classify those patterns between something which is okay, which is not okay. So one of the typical use cases people come to us is that unknown anomalies, anything which is we haven't seen before. Can your model do this? And the point here is that without training data. So one of the key work we've done is by training this pre-trained model, which we call it understanding physics. It's not really knows laws of physics. We didn't have any inductive bias in these models, but we train a very large amount of data. So it's generalizes to sensors and generalizes to physical effects and generalizes to behaviors it has been trained on. So, and that's where this capable of generalizability and not having to bring your own data and train the model, fine-tune the model, and still the model can give you performance within the boundaries of what it can. That's how we solve this broad fragmentation of data in across these industries. Now, I completely agree with comments that in the physical world, when you do manual operation tasks, like putting some expensive product or driving the car, the cost of error is extremely high, and it has to work 100%. When the decision making is left to human, and you're amplifying human decision making, 100% is not required. So your bar is a little bit lower. It's not 60, it's not 80, but it doesn't have to be 100%. It can be within like 90 or something like that. So we are fundamentally dealing with, we don't have to reach this super like 100% accuracy targets, because we're building dialogue systems where people can actually work together with the AI system we're building and be able to fine tune with their answers in the real time. So this conversational element of physical AI system we're building, and also generalization capability of the model, allow us to apply the same model, the same pre-architecture across a very broad range of fields. So we're working literally from automotive to semiconductor, to the electrical grids, to drilling and oil, using the same model. And that's sort of, for most of these companies, actually, it's a huge advantage, because they simply don't have capability to build specific model for every sensor, every task, every anomaly, and so forth. So that's how we're approaching this approach, and we call the model Newton, because I like the name.
Thanks, Ivan. Yeah, really impressive, the range of use cases that Newton can tackle. And there's one other comment Colton made about you leveraging some of these models for labeling and for synthetic data generation. And I know that Skydio is an Encord customer, Ulrik. So I wanted to know, is that, are those approaches relatively consistent with what you're seeing with other customers?
Yeah, I mean, I think they definitely are. I mean, I think most of the labeling work that will be done in the future is going to be around the edges of the distribution, which I think they already are to an extent. So to Kalpana's point earlier, right, like a lot of the sort of grunt work that was done in the past with like large workforces like overseas labeling a bunch of data and sending it back, I think those days are probably like, I mean, I don't know if they're coming to an end. People have been saying that for 5 years, but at least like that market is going to change a lot, because it becomes much more about like, yeah, finding like the relevant data for the next iteration of the model. And that kind of goes back to the point I made about earlier about integrating like your AI system with like whatever your, application is in the real world. And of course, like OpenAI has done a great job of that, right? Because they now have 500 million people that are providing real-time feedback on ChatGPT. But for, I think, any of the panelists here, that's much more difficult, because you have to do this on the edge in like very compute constrained environments, and there are other like different types of problems you need to solve doing that.
Let's get to some specific use cases. Maybe we could go down the line, and each of you could talk about either a use case or a customer story that you came across that really changed the way you think about physical AI as possible.
Sure. Yeah. Maybe I'll share a couple of use cases. One is around DFR, which is a drone as a first responder program, which has been taken up by a lot of police departments around the country, including here in San Francisco. And our drones are being used in a lot of search and rescue operations. And to me, these are real heartwarming stories because the drone is essentially allowing police officers to be able to very quickly find people in situations where, for example, they may be in harm. There are some stories, for example, where people lost in cornfields were found within days and minutes and were given the medical help that they needed when they had some sort of injury. Cases of missing children, drones being used to basically do these types of operations, and seeing robots in the real world actually helping save lives is something that's incredible for me. On the other side is a lot of our customers who are doing inspection and monitoring types of use cases. This includes things like BNSF. They are a rail yard operator, and they use our drones, for example, for inventory and asset management. And these drones are just continuously performing missions, identifying the different containers in the yards, locating them, so that you at real time have an inventory and know exactly where each of your assets are. Also inspections around Caltrans, doing inspections for roadway construction, inspections of power lines, miles and miles of power lines that need to be inspected so that we have safety critical, we do not have safety issues with these sort of systems. So I think these are all use cases where it's great to see the robots actually bringing value to society.
Thanks a lot.
Yeah, I don't know if there's like a single use case, but I think the thing that made me kind of change my mind on physical AI the most, or at least like when I kind of understood the value, was when someone told me they're building a foundation model also for robotics, but instead of having the text be the prompt is the pixels. And I think the panelists here could probably resonate with that, where the prompt basically becomes like an image, right, of picking up a sponge, or it could be anything. It could be like search and rescue or whatever. And based on that sort of like context, the model is able to automatically like plan what it is supposed to do in that specific scenario. So like changing the mindset of like away from prompts as pure text to prompts as pixels, I think was something that like at least like took me a while to internalize. But once I kind of like understood it, it was like, wow, this is going to be quite substantial in the future.
I talk about couple of use cases, I think, and I want to say, first of all, most of the use cases coming from our customers are extremely boring. They, like I think like robotics, everybody's excited about robotics because, we all read children books about the, or watch the cartoon Astro Boy or something like that, and we can imagine this robots is so going to be cool. But most of the people who are trying to like keep the world running and just keep the world operating and provide electricity, provide water, provide like food, provide things, there is a very critical piece of that, and it's not that exciting. So one customer we have is, and we kind of deep in work with these guys, they're running windmills and wind turbines in Latin America, providing electricity to people. And every wind turbine has, I mentioned this example before, have about 40 kinds of sensor and integrated sensor in each wind turbine, altogether 120 sensors per wind turbine. And whenever a wind turbine shuts down, and they have to shut down, they have to buy electricity on the secondary market. And its price for electricity on the secondary market is 10 times more what this turbine's producing. And they have to provide, but at a lower cost, which they agreed with the customers. So everything goes wrong with those turbines, those 65 turbines. A bird hits the turbine, a transformer blows out, something else happens. The cost of electricity for this company goes astronomically, and if they can go out of business fundamentally, and then whole area is going to be without electricity. So for them, the guy who runs this whole thing, he's actually in Costa Rica. He told us like every sensor he invested in his wind turbines is giving him 10 times return, because stability of operations 100%. So for them, be able to look not just like every sensor individually, but look at multivariate anomaly detection analysis, where you have a multiple sensor. I'll give you an example. You have a torque measurement and you have a electricity produced measurement. And each of them could be okay, but combination of them is not. So be able to find these multivariate anomalies and do it quickly without spending hundreds of thousands of dollars training the models, for them is kind of a godsend. And it's sort of like basically providing electricity to the massive areas in the country. So this is kind of like a huge number of, and they're willing to pay, by the way, because it's a real money business. It's very similar. We have conversations with like companies like Applied Materials. It's very simple problems but just like be able to build generative models which can work with this data directly is huge. A little bit more aspirational use case, we have this working with University of South California, with orthopedics department and the people who are working on recovery of people after knee replacement surgery. So whenever, if anybody wants knee replaced, talk to me, I'll hook you up. So the recovery after knee replacement surgery is a huge process. If recovery doesn't go well, if you overload your knee, then you will get inflammation. You have to do corrective surgery, which is about like 10 times more expensive than putting the knee there, right? Or you may even lose a leg, if in the worst case scenarios. If you don't load your leg enough, then most probably you would not get healing at the right time, the right thing. So the bone grows when you load it up, right? It doesn't grow when you're just laying down on the couch. So you have to walk, but if you feel too much, is bad. So be able to kind of like understand the recovery is critical, important. Also, the way you walk is, and you can capture the way you work. You can detect diseases such as Parkinson, Alzheimer, stroke, depression. Like everything can be captured by the way you move in the world. And we were working with, and it's kind of, we're working with UCSF on kind of like, we showed them, they never knew that. We showed them that by placing few sensors on the leg and measuring patterns and feeding through our models, you start clustering that without having to actually capture data for people who have a stroke. Because usually you have to capture data from people with stroke. Getting these patients is impossible, collecting this is impossible. You have all these regulations. And like, look, you don't need to do this because we have a general mechanical model which can do that. And they're studying this whole motion right now in medical field, which they call motion as a vital sign. So there's a whole group of medical professionals around the world right now trying to build a network of people collecting normative walking data, and using normative walking data, using Newton to train this version of Newton, which will be able to detect on early variations of normative walking, depending on the age, gender, and everything else, and give you opportunity to early detections of all these diseases just from walking. And there's a big motion, big movement. They go to the conference in Berlin. We go and show stuff. So this is really exciting, and it's example how, again, this kind of models can actually save people's lives and
Thanks, Stefan.
So use cases. I think my problem in all this is to me is just for robotics manipulation, what humans can do, what OR should be able to do at some point. The spectrum is crazy. This is what people can do, and how to focus on these things is really, really hard. And I think in Intrinsic, we have especially a lot of time. Where should we focus? If we would like to create a platform for all robotics, that means we have to provide libraries, features, APIs, but also which allow you to do these things, and it is just too much out there. So there's household tasks, there's industrial tasks, but it's a more complicated industrial or household. Maybe we could make household tasks that were sexy for some reasons, because people can relate to them anymore. Industrial tasks are incredibly versatile, what people can do and what they have to do in order to do whatever manufacturing tasks they're doing. So I'm perplexed by the breadth of all this here. There's not really anything here I feel that robotics has made a transformative change at all so far, which is really annoying. There's little high execution, BI with a large engineering, really cool robots, which can do something. A lot of very focus. I don't know what it is, as you mentioned. It's also fantastic, very focused. But can you see the breadth of tasks between everywhere is really But one example which I find it is very fascinating is essentially multi-arm manipulation of flexible objects. Where two or multiple arms, who cares about two? Okay, just because we use that, so could be four, and arms have to help together doing something. Particularly the object are not really body, it's outside of the standard perception techniques. And they need force control, a dual arm force control, and getting things done nicely. If you do this, you do this every day perfectly well, without any problems. You can do it with a partner with 4 hands. You can do it with a partner for 6 hands. This is kind of a domain where you don't really know our culture, that it will go to it, but it's just happy thing. We expect that.
Oh, as far as use case, honestly, it's just my excuse to get a chance to eat incredibly sweet and fresh strawberries. Yeah. Seemingly everything that fly needs 47 and less than us is that, yeah, a good supply for the strawberries.
Strawberry seasons. Okay.
But I mean, I think more seriously, it's nice to be working on an application that honestly everybody wants the solution, and there's no contention around it. You know, the farmers obviously, labor is increasingly expensive and really hard to come by. Even the workers themselves who work alongside our robots, they are every week they ask me, "Is it ready yet? Is it there?" Because they're in their 60s and 70s, doing backbreaking work, 60 hours a week. So they don't want to do that task, and they do it. Their kids are not coming in as well. And so, insofar as robotics having the opportunity to do something meaningful that really nobody wants to do, it's really not taking away any job. That's kind of what's rewarding for me and my team. At the same time, it comes back to the point about that people have heard this promise and this story for a long time. In the strawberry picking space, for instance, it's honestly littered with carcasses of failed startups that tried to do strawberry picking and not succeeded. And so there's no point in that regard. There's no point going to trade shows and trying to go out marketing. And especially, and I think maybe a space like coming back to sort of use case application, space like agriculture forces you to really believe, remind yourself that it's not about what marketing that you do. It's does it actually work? Because these are farmers, right? And it affects their livelihoods, it affects, and they need a product that actually work. And if you can make something work, then the rest will take out.
Thanks, RJ. So now time to put our panelists a bit on the spot here with a nice prediction kind of question here. And so kind of let's do a lightning round from RJ down back to me. Where are we in the journey to prime time physical AI? Like, are we in maybe the early innings, the scaling phase, or are we almost at prime time? And what is prime time?
Extremely early, and even the self-driving car is like a tiny fraction. What is prime time? I think I guess an example of what you see in SF today, where no one bats an eyelid of a driverless Waymo going around, and that for all different applications. But I think 10 years, at least 10 years away.
Okay, where are we? I think we're in an interesting incline. There might be a little bit of pop coming up. It's kind of the AI quality called pop. It's not so unlikely that there will be a little bit of a dip afterwards. On the other hand, we do need robots, automation, AI. The world of manufacturing, all the prediction says, and I say is given into huge growers because people don't want to do these jobs anymore. And we have to change something a lot. So there is clearly very interesting incentive and in the parts of financial incentive to do something really profound. Just how could the AI will be years and this word will train on this one rapid and not giving it and see it in the wise sense and I would love to see it at some point. But when you might be popping first before you go back to something more.
We don't do robotics. Did I mention that? So well, I think we see our deployment will happening very quickly because what you said, by the way. The biggest reason people come to us in the manufacturing field, and we just finished project with Kojima, big construction company. Number one problem, people don't want to, go in the field and dig big holes in the ground and this and all of that. So there is but there's also there's a lot of overhead to controlling those systems. So, and it is a way to make these operations, there's two ways. You can get robots there and run and kind of automate certain things. But another thing is you can have existing people more efficient. and there was a huge need, a huge request from the from industry and variety of fields. How can we make what we have now significantly more efficient? What would be the way to do that? So, and I think physical AI, in our definition, would be a game changer for all this industry. It can completely change the way all of industries work and make existing capital and existing people working in the field dramatically more efficient. We want to build a superhuman, fundamentally. If you ask me what our goal is, to build a superhuman, not to build better robots. It's philosophical divide. I would like our team fundamentally. We don't hire people who come from robotics field. It was to stay away from them. And it's all about like human amplification. How to make people dramatically smarter, dramatically better. How to give them tools to really amplify them. That's sort of a vision behind the company.
Yeah, I think for me, I think where we are now reminds me a lot about where we were with natural language processing and large language models. They weren't called that at the time. Back in like 2018, 2019, that was when the BERT models were very popular for NLP. I think the first or the second GPT model had just come out, and it was also like just right after the Transformer paper came out in 2017. And so I think that's probably where we are, which is about LLMs 5 years ago, give or take 5 or 6 years. I think for prime time to happen, well, I think we have to have like a kind of like ChatGPT moment, right, where we have this like product that just like illuminates everybody's eyes to the promise of physical AI, and like what that looks like, I don't know, but to have that sort of like integrated feedback loop between humans and the models and the systems, I think that's like how we're going to be seeing this like exponential curve. And I think there's some ways away from that, because I think to RJ's point, when I take my Waymo in the morning, right, it takes like a 20-minute detour because it has to go around this like road work on the way, which like feels like it shouldn't be doing. So once it kind of learns how to pass that, I know we've made good progress.
Yeah, I think I agree with everybody else. We do have robots operating at scale, but I think we're still in the early stages here. I think oftentimes we still see that our drones in particular are used as tools by human operators, human pilots who are trying to accomplish some tasks. We have a lot of assistive features and technologies that they use there, like obstacle avoidance or semantic understanding of the scene. But the human is still sort of piloting and performing the task. We also have autonomous missions that are often used by a lot of our customers, but oftentimes that again involves human thinking around what is the operation that they wanted to perform, what was the mission they were trying to execute, setting waypoints, having some digital twin of the infrastructure they had set, trying to inspect and so on, all of which could potentially be replaced and be just understood by the robot. But I don't think we are quite there yet. And then the final thing, as Ulrik said, is human-robot interaction as well as multi-robot interaction to be able to collaboratively perform tasks, which is also, I think, sort of a frontier.
And Kalpana, RJ had mentioned, a goal of like, kind of L5 autonomy. What and it sounds like in your answer there, you say we're not maybe fully to our full potential of autonomy. What is missing? What will help us get to that kind of level 5, or whatever that is for Skydio?
I think time and more research and more deployments and learning. I think one thing that we would, I think somebody mentioned this before as well, zero shot or few shot learning and end-to-end learning from the types of missions and tasks that we are performing today should hopefully get us there. I think safety and reliability is another sort of barrier that we need to overcome. I think today we are in a much better place, at least with the products we have at Skydio than maybe 9 years ago when the company started. And getting that final, going from the 90 to the 99 to the 99.99 is always going to be a challenge, I think. So I don't know if I have an answer to how we get there.
Sure. And maybe we could just close it off with Ivan. I think you painted a picture of like this kind of a superhuman. Can you like kind of expand on that idea a bit for us of like, the concept of replacing humans versus, enhancing them and providing recommendations?
I think this is like foundational since like um, if you think about like since like the development of computers, there's like two school of thoughts. Either you're creating a amplification of human capabilities and adding kind of like to humans capabilities, or you creating a artificial sort of like intelligence, artificial humans, artificial kind of um, artificial replacement. And I think this two school of thoughts has been, I don't know, since 60s. Um, uh, Steve Jobs famously described his computer as a bicycle for bicycle for your mind, as something which you can amplify your capability with the help of technology. And we believe, like in our company, we follow the same tradition of amplification of humans' capabilities with a technology which is incredibly powerful, which is modern artificial intelligence. Where this goes into the, of course, the interface between humans and machines right now is pretty rudimentary. We're using eyes. Would it go further when this kind of AI technology is going to be built into the humans? Are we going to get chips? Is Elon Musk going to get his way and everybody get a chip in the head? That remains to know. But the form and shape, we'll see what happens. But at the same time, I do believe that creating autonomous robotic systems is going to be second direction, and it's also unavoidable. It's yet to be seen whether we go through humanoid style robotics or specialized robotics, which specifically built for specific tasks. That's whole different directions which we also pursuing. And I think at the end, I see these two directions merging together, where you will start thinking about robotics factories and robotic cities and robotics houses and autonomous robotics moving within this environment and be able to communicate effortlessly with sensing fused systems will live around us, and humans being part of that complex environment where all those three systems, robotic environments, autonomous robotics, and humans working together. So this is sort of thing, this is further down, future down the line. But I think we're building right now these pieces, and it's a really exciting time for that.
Yeah, thanks much, everybody, for joining us on this panel, and thank you, Kurt, for inviting